Okay, hello and welcome to the next set of lessons for Key Stage 4 Look at Energy. What we've done here, we've actually combined lessons 4 and 5. So what we've actually, obviously the last lesson, we combined lessons 2 and 3, so we looked at heat transfer and we looked at thermal radiation. What we're going to have a look at today is reducing heat loss. And also, we're going to have another look back at a topic that was in Key Stage 3, which was the energy transfer diagrams and working out energy efficiency as well. Now, if energy transfer diagrams, the ideas of sankey diagrams, you're not really sure what they are, I would recommend you go back and look at Key Stage 3. One of the set of 6 lessons that we did there. I will be making references back to it, but to get a more fundamental look at it, you may want to go back to Key Stage 3. But anyway, let's start having a look at heat loss. So, reducing heat loss, obviously we were talking about energy sources. We said in our last lesson that we were going to have a look at how we can reduce heat, not necessarily just from ourselves, but how we can reduce heat from, say, from a house or so. So, surprise, surprise, we have a nice thermal image of a house. So, the way this thermal image works is that the red, all the things that are red are where the most heat is being lost. Yellow, not so much heat, and as it gets darker, so your blues and your blacks up here, there's not much heat at all. So, how do you lose heat from your house? Basically, you can lose it from the 3 fundamental ways that we explained previously in these lessons from the heat transfer. So it can either be from convection, conduction, or from thermal radiation. So don't forget, thermal radiation, although it is the biggest source is from the sun, everything that is hot or anything that has heat thermal energy can emit thermal radiation. So how can we reduce the heat loss from this house? So as you can see, there's lots of heat being lost from these windows. So that would suggest to me that they're single glazed windows. Now, double glazing windows, you have 2 panes of glass and you have air in between. Now, remember what we said about air, because the molecules are so far away from each other in air, they're not very good at conducting heat. So they're actually quite a good insulator. So you actually have that in double glazing windows. That's why most houses have double glazing windows, it's actually to keep heat in. As you see, there's a lot of heat up in the loft, or up in your attic. This again could actually have insulation done across the inside of the roof. This again could be made of other insulating materials, or again actually different packings of air, same as you would have cavity in between cavities between 2 sets of walls. All of these can be good for reducing heat loss within a house. So how does that mean? The conduction, obviously as we said, is the heating of molecules in a solid material. So as the heating from the outside, this can be used, it's not just metals, although metals are the particularly good ones at conducting heat. In this case, even in the molecules in bricks, or even in the mortar that makes up the bricks in between the bricks. The molecules in air are vibrating as well, so those themselves, the heat will gradually travel through them and be lost to the outside. With convection, if you've got any spaces in between your windows or in your doors, cold air can come in, the heat will be rising up, and if there's not insulation at the top, then the heat will rise straight out the top of your house, the same as it will come out the top floors, out the windows. And thermal radiation, again, same as I said at the very start of this, that every single object itself, if it's hot enough, will emit thermal radiation. Okay, so that's a quick look at reducing heat loss in the building. So what can we do about losing heat loss in ourselves? So this is our dent again, he's back, we had him in our last lesson. So as we explained before, is that clothing, as we were looking here, on his clothing, again, it's very similar scale to what we have in the house. The brighter the colour, the more heat that's being lost. So you can see he's losing a lot of heat from his face. Not so much on the top of his head, and it's not just because he's got hair there, but it's because there's actually air trapped in between your hair. So that hair itself is acting as an insulator, so you lose less heat from your head. And again here from the t-shirt, or from his shirt that he's wearing, the darker colours or sections of the shirt that's not actually touching his body. Whereas the bits that are touching his body, here, they're much brighter colours. So that actually means it's the air in between the fabric and the body that's acting as an insulator to keep his body warmth in. So really, the idea of keeping body warmth into yourself is actually having clothes that are made up or have air in them. So that's why you see, in the winter you wear big puffy jackets, because although there's lots of material in there, there's air acting in there as well as insulators as well as that. And the materials needs to be much more thickly woven, so the clothing, the actual material itself is a lot denser. That will also help to reduce heat. From your head, hat's always a good idea, isn't it really? Woolly hats themselves, again, lots of material, and with trapping air into them as well, that themselves, act as an insulator. So that was our quick look at reducing heat loss. So the other section of this lesson today is looking at energy transfer diagrams. Now, if you don't recognise this kind of energy transfer diagram, this is where you do need to go back to key stage 3, because this is just our energy input, which is being transferred via a process. In this case, it's a chemical process, because it's a car engine, which is then resulting in an energy output. Now this, as we said before, is the energy transfer diagram only shows the useful energy transfer. It doesn't show the non-useful energy transfer. And this is a point where I'd like to actually put in the idea of the conservation of energy. Now I know I've mentioned it before in previous lessons, but this is where it needs to come in really, because we must remember that for any energy input into a system, there will be an equal energy output from that system as well, because energy cannot be lost or destroyed. It may not be used in the way that we want it to be used, but it will be used up in some way. So this is the point we're going to try and get to today. So here we're moving on to our Sankey diagrams. Now this itself, again, shows us not just the useful energy. This is actually an idea or the concept of energy going into a light bulb. Again, which you might notice, we've used a key stage 3. So this is obviously the total energy that we have coming in here. In this case, it's 100 joules. And what we actually have coming out here must match the same amount of energy that we've got coming in, because remember, the amount of energy going into a system must equal the energy going out. So the useful energy, the energy of this 100 joules that we're using that's actually going to light our light bulb here, is actually only 10 joules. So where's the other 90 joules gone? We can't just lost, it can't get destroyed. It's down here, and it's been taken up as our non-useful energy, which is actually coming out as 90 joules. So this is just an old light bulb. Now obviously new light bulbs are called energy efficient light bulbs, because guess what they do? They use the energy better. So here we actually have, again, we have 100 joules coming in, but in this case, because it's our energy saving light bulb, we've actually got 75 joules being used as the useful energy, so actually lighting up and producing light for us, with only 25 joules itself being used as non-useful energy. So I hope that gives a brief concept of the idea of conservation of energy. Just remember that, as I said, any energy going into a system, the same energy going out of it must be the same in total. So the useful and the non-useful energy must equal the same as the original energy that's coming. So the final thing that we're going to look at is efficiency. Now we briefly mentioned this at key stage 3. Luckily we've got some nice numbers here which are going to work out quite easily for us. So what we're taking is our energy saving light bulb again, and efficiency is basically the idea of how much of that energy is being used as useful energy compared to the energy that's being lost as non-useful energy. So as we said before, all the energy obviously must be accounted for. So efficiency equals the power output, so our useful energy, compared to our total power input, so the amount of energy actually coming into the system. So as we said, that actually is divided by each other, and then to get a percentage, because efficiency is measured as a percentage, we then have to times that by 100 to give our percentage. So how does that actually work out? So as we said, our energy going in is 100 joules. That's our total energy going in. And our useful energy that's actually coming out as light is 75 joules. So what we need to do is we need to take our 75 joules from here, and we need to divide it by our total energy going in, which was 100 joules. Now, while you work that out, I can tell you that it comes out at 0.75. So what we need to do to work that out as a percentage is that number itself, we just need to times it by 100, and this will give us 75%. So that means that our energy saving light bulb has an efficiency of 75%. So this is obviously much better, because if we go back to our original light bulb, which was which was 100 going in with only 10 actually being used as the original energy source. So that's 100 here, and with only 10 here, so that would actually work out that we have our 10 joules over our 100 joules going in, which would actually give us 0.1. So then that times by 100 gives our efficiency of only 10%. So we can see that our energy efficiency for our energy efficient light bulb is 75%, so it's 65% more efficient than our original light bulb. Okay, so that was our look at heat loss, energy transfer diagrams and energy efficiency. So we've had a look at reducing heat loss in insulators, both of buildings and of people, and we've had a recap on our diagrams, our energy transfer diagrams and our Sankey diagrams, and the actual maths involved in efficiency. Okay, so that's the end of today's lessons. Next lesson is actually going to be on the start of 3 lessons are actually looking at generating electricity. The first one we're going to be looking at is generating electricity from fossil fuels and from nuclear power. Okay, thank you.